So everyone, I want to teach you guys about how you can make your binary smaller by using C++ exceptions. So a little about me. If you've seen the name CppCon anywhere around, that's probably me. I use that username for almost everything. So a little bit about myself. Graduated from San Jose State in 2017. I'm an ex-Googler. I worked on a couple of products that you might have heard of. The Google Pixel Watch, the original. I was the directly responsible engineer for the haptics and the bootloader and the speaker and the microphone. And eventually when I got tired of that, I moved over to the Google Pixel Buds and worked on code optimization so we could fit more features and bug fixes into the device. I'm also a volunteer at San Jose State University, and I primarily help out with the robotics team at San Jose State. And I'm also an ISO C++ member since last year. Before we go any further, I want to go over the motivation for why this talk even exists and how I got to this point. So about 6 years ago, I was teaching a class called Computer Engineering 146. It's Intro to Embedded Systems. In this class, I developed a firmware framework for my students. It was written in C++. We followed the C++ core guidelines as close as we could. And just a little shout out, this is a board that I designed here for my students to use for the development. The first thing that I teach a lot of my students is that when you're developing for microcontrollers and doing bare metal development, you don't have an operating system. That means you don't have access to fopen. You don't have a file system. You don't have networking. You don't have a terminal to print to. You don't even have a clock or even threads. If you want any of those things, you need to implement them yourself or bring in a library that can do it for you. But there's another little caveat to this. You can bring in all those libraries, but there's only so much memory available. Here is a Google search or a bit of a search on a website called DigiKey. If you know embedded systems, you know this website. You can buy a variety of different electronic components, including microcontrollers on these. If you look at the devices that are less than a megabyte in size, you get about 33,000 of them. If you look at the devices that are above a megabyte, you get about 5,000. So there's not that many devices with more than a megabyte worth of flash memory. The same goes with RAM. When it comes to your RAM, it's only about 100, if you look for things that are below 100 kilobytes, it's about 31,000 of them. Above that though, 7,000. So again, not that many devices that support really large amounts of memory and RAM. So with so little memory, how do we prevent running out of memory or memory fragmentation? In general, we will try to avoid, or if not completely ban, dynamic memory allocation. So free, new, calloc, delete, all those things we tend to try to not use. That also means containers that use those mechanisms are also kind of off limits, although I've been told many times by many other embedded developers, well, hold on, we do use dynamic memory allocation just at initialization, and that is true. You can init all your stuff at first, so long as you're not deleting or reallocating later on. If you need containers in the embedded space that either own their own memory and don't heap allocate, you can use the embedded template library. It's called the ETL. But we have standard in-place vector, which was voted into C++26 at St. Louis about a couple months ago. And this would be your example of something in the standard library that you could use in embedded systems that owns its own memory and is a try push back, so you can actually test to see if you've exceeded your allocated memory. So given those constraints, let's talk about the reasons why the firmware developers don't use C++ exceptions. Number one, requires malloc. Gotta dynamically allocate your exceptions. That's kind of a bummer, that sucks, so that's one of the issues. I've also heard from other people that it's unbounded memory usage. If you start using exceptions, you can't tell how much memory is going to allocate. There's also the issue of increased binary sizes. I had one individual tell me that if you use exceptions, it brings in the entire STL, all string, vector, everything gets brought into your binary. Can't handle that. It's too much memory being used up. It also, a lot of people know about this, it brings in runtime type information. And that could use up a lot of valuable space that we don't really have on these embedded systems. Also, there's these things called the exception tables, and even the exception code itself is quite complicated, so that ends up using up a lot of memory. And on the time side, we have the non-determinism issue, mostly from dynamic cast and maybe some other areas. I keep this one down here secret just because if I tell you, it might give too much off for my next following talk, so I'm not going to tell you too much about that. And then finally, it can be slow. There's binary searches that are required for this. There's the frame unwinding, which can be complicated, and there's the frame evaluation, which can also be complex, which can be costly in terms of time. But let's get back to class for a sec. So in my class, I built a whole bunch of different libraries for my students, and also built these interfaces that they could use to guide them through developing drivers. We're going to go over one in particular, a very basic one called the output pin. So if you've never seen a microcontroller before in your life, here we have this little black box with a little bit of lettering on it, and these little metal extrusions that come out. We call those microcontroller pins. some of which might be output pins. With an output pin, you can set its state to either a low voltage or to a high voltage. In this case, the voltage is low, so there's no potential difference between the ground position and this pin. Therefore, no current flows. Set it to a high voltage. Now there's a potential difference. Current can flow. LED turns on. Great. We can now turn it on and off an LED. You can use output pins for a variety of things, but the basic thing that people usually show is an LED. So to me, I'm like, all right, well, if I'm building an interface for this, I mean, if I'm just going to be able to turn something on and off, I just need a simple function, level, give it a true-false value, a bool. If it's true, turn it high. If it's false, turn it low. Simple enough. But when I made this, I wasn't sure if returning void was okay. I was thinking to myself, well, what would I need to return? Well, there's no information I'm going to get out of this. Maybe an error state of some sort, but what type of errors could come from this? I built so many different libraries for microcontrollers that most of the time this particular function is infallible. There's no way it's really going to fail. But to kind of show how it could fail, let's introduce another concept in embedded systems. I²C. If you know embedded systems, you've interacted with this countless times. If you don't, I want to go over a quick primer. I²C is a bus protocol. It uses 2 pins in order to transmit data between multiple devices. In I²C, there's the concept of a controller and a device, where the controller is able to initiate conversations on the bus, and the devices can only speak when spoken to. Those conversations start off like this. The controller will create a start signal. This will create an intention signal to everyone else saying, hey, listen up, I'm going to speak out, look for your address. Then we present an address along with a read and write signal. The device that corresponds to that address must acknowledge that request and allow the transfer to continue. If the device is not on the bus or can't handle that type of request, then it will not acknowledge. Now the way the transfer works is that after you've acknowledged if the controller is writing to the device, the controller will write a byte, the other device will acknowledge, writes another byte, acknowledges, so on and so forth. On the flip side, if you're reading from the device, the device will write the byte onto the bus, and the controller will acknowledge, so on and so forth until it's complete. Now, why did I bring this up? Well, there's a couple of errors that could come with I²C. Specifically, address not acknowledge and an IO error. Now, for address not acknowledge, in some cases, not a big deal. For example, I've seen hot swappable systems where you can plug in I2C devices, and if they're not there at the moment, that's fine. If they are there later on, that's okay. But if you're writing software for a drone, and the sensor you use to keep your orientation and keep you afloat just stops acknowledging you, you're going to plummet to the ground, unless you have like a parachute or something like that. And then IO errors can come from electromagnetic interference. They can also come from other devices on the bus that are erroneously controlling the lines in some weird way. Now, how do we fuse these two together? Wow, that was a good catch. Let's consider a thing called an IO expander. This is a device that you would use for your microcontroller if you run out of pins. I want more IO, I want more output control pins, but I do not have the necessary pins on my device. So I can communicate over I²C to this device here and be able to tell it, hey, I want you to set your pin 0 to a high or a low voltage. But here comes the rub. The I2C side is a fallible interface, and the output pin is an infallible interface, at least the way that I wrote it prior. So to kind of illustrate the problem, let's say we have a really simple function called IO expander level. It returns back a bool. It's true if it's successful and false if it failed. You give it the pin, you give it what voltage level you want, and you run from there. I have some implementation that's going to do it. But what do we do when we're not successful? Well, because we can't use exceptions, remember, there really isn't much I can do. I can set a global variable, or I can set some state within the object and then have another function call that object's function, or call a status function to see, hey, was this successful? The thing I don't like about that, though, well, setting up error no is not a good option. We all kind of figured that part out. And I don't think that using an internal variable and having to call an out-of-line function is as any better than error no. So then I was like, okay, but is this a real big problem? So I considered the use cases that my students might use these output pins in. Let's say they're going to control an LED. Well, I think in most cases, controlling an LED is not that big a deal. If the LED doesn't turn on, I mean, maybe the customer's a little upset. But it might be a problem if that LED is like for your check engine light. Okay. How about for a heating element? Well, if it's used to control a chemical reaction of some sort, that could be a problem if you can't get that to work properly. And then I thought, well, what about an emergency cutoff relay? At the very least, you might not be able to do anything about this, but at the very least, we can tell you that something went wrong when you tried to attempt this action. So when I realized that this was an issue, I decided to switch all my APIs to use std_expected. I made my own little type here where we have a status, which is the expected type is void, and the error type's my little enumeration. And then here we return back bool. For those who are not familiar with std_expected, it is a type that can be either or a actual result or some error type. In the example here, let's say we are trying to get some version from some particular device. Device is not connected. We can return back the precondition has been violated and use standard unexpected to create the error state of that object. Or you can just return back the number. Obviously, this is like slideware, it's very simple, but that's kind of the idea. So then I thought to myself, okay, I don't just write APIs and just forget about them. I want to think about how do my students or how people who are my users going to use my APIs. So I was like, all right, well, if I used exceptions, this is how my code would look. If I wanted to toggle an LED, pass it a pin, pass it the amount of time, set it high, wait a certain time, set it low, wait a certain time, we're good. If you used std_expected before, you'd expect that the code would look like this next, where for every single one of these function calls, I need to check to see whether or not the status of that return was successful. Otherwise, return back an unexpected value and propagate up the error that you acquired. Here's another option. It doesn't exist in C++ currently, but I was really excited when I saw this. It is the error propagator from P2561, R1. It uses a double question mark. It's similar to Rust's question mark operator, which automatically propagates errors up your stack. I remember emailing the individual who was working on this and never got anything back. And maybe that was a good thing, because it would have caused me to not go and do the research that I did currently. So I didn't have this, so what can I use? A macro. There's no other real way in C++ to do this. And if you have a way, please tell me, I'd like to know. But I just came up with a quick little macro, sj check, does all the checks for you, looks almost identical to the question mark option. Just a little bit. So then I had to ask myself, which APIs need to return errors? And the answer to that is almost all of them, because I had made interfaces for motors. And look at this, here's a motor controller that talks over I²C. All right, and then what about this? This is a display that talks over I²C. Almost everything can be represented or communicated over through I²C. So I have this explosion of how anything can be implemented with I²C, therefore anything can have an error propagate from underneath it. I could have separated out the types to have one for infallible and non-fallible, but I didn't really like that paradigm. So I moved almost everything over to std_expected. And here's what 2.5 years of doing this to my students caused. Here's what they thought. Number one, they hated all the if statements that they had to write everywhere, to the point where my students got clever and started void casting away all the errors. So much so that it was actually kind of sad. One of my students spent like a week on this particular problem, and I looked at their code and I was like, hey, you're not propagating the errors. Maybe this one little area here could be fixed up. So we refactored our code, took a while, but we factored all the code and we propagated all the errors, and we found, oh yeah, you're using the wrong address. And that's the reason why you're getting an error here, but that's the reason why your code isn't working. So this took time out of her day. The other thing they were annoyed about was the virality. Every one of my students was like, man, I gotta make every single thing return back status or results every single time. If I wanna call anything that could potentially be fallible, I gotta put it everywhere. It's everywhere, and it touches everything. And they found that the macros, at least, were quite noisy, because what you actually have to do when you look at this code is do this. Try to blank out the sections that have the macros so you can just see into what's really happening in your code. You don't care about the sad path. You want to know at least what the happy path does, and then you can go over and look at what the sad path does later on. So they had to do a lot of this. Every single semester, my students would always ask me, why not just use C++ exceptions? They're built into the language, they're meant for error handling, wouldn't that get rid of a lot of the problems that we're dealing with? And I would verbally tell them this diagram in its totality. I bring up articles, I bring up things that I found online, I would even change the build script to go from F no exceptions to F exceptions and show it blow up and say, here, there you go. This is awful, why would you use this? Most accepted this, but some continue to ask why. Like, why is it non-deterministic? Why is it so slow? Why does it have to be slow? Why does it have to blow up my code? And why does it need heap? And again, I would figure out ways to answer these questions, and they'd accept them, but I started to not accept them over time. I did not like the idea that I was telling my students this information about why you shouldn't use something, but I don't know how it works. It's a black box to me. I just know what I've been told from other people. And I started feeling guilty for telling my students not to use this thing because I didn't know exactly why I couldn't use this thing. So I told myself, you know what? I'm going to give exceptions a full shake. We're going to go all the way with exceptions. So now we're going to make exceptions work on ARM. I'm going to go over the steps of what you have to do to make it work on ARM because it's not trivial. Here's what I want to do. I have a function called main. It just calls a function called start. It throws something. I don't inline it because otherwise the compiler gets smart and get rid of all my code. And I just want to end up in this catch block here. I want to end up in this little return area. First barrier you will encounter is that exceptions are default disabled when you run your program. If you download the GNU ARM toolchain, it'll be disabled. Anytime you try to throw, you immediately terminate. Anytime. Doesn't matter how valid your code is, it will always terminate. The sad part about this is that ARM will still bring in all of the libraries and everything else that it needs in order to run exceptions, except it just sets it up so that it always terminates. So it bloats your code and does nothing, as far as I'm concerned. Yeah. So the first thing I needed to do was break down this barrier. How do I enable exceptions or figure out if it's even possible? They changed their instructions a while back. I used to list them off, but it's so different now that I can't really explain it to you because I don't know how to do it. But basically, you download the toolchain, you find whichever file has no exceptions in it, and then you change it to exceptions. You recompile it. It should almost work. You need to do one last thing, which is to set break. It's a low-level C API, which provides memory to malloc. Once you provide that, exceptions work. But there's one other issue. Your binary size is now massive. Check this out. 150,000 bytes. I went from 2.6K, and now my binary is blown up. I only have a half a megabyte of memory to do my application. And this is going to eat up 30% so I can throw and catch? Nah, I'm good. If that's how life's going to be, oops, then I don't want to use this. So that was my issue. But I was like, but why is it so big? So next barrier to break, eliminating the bloat. See if there's any way we can get rid of that bloat somehow. So I do the only thing that makes sense to me in all the work I've done in the past, which is you disassemble the code and you look for anything that you did not write. That would probably come from, especially since the code was so simple, it would come from the compiler at this point. And when you look in, it might be a little hard to see, but I saw this API called global string callback adapter. I don't have any strings in my code. What is this doing here? You look around a little more and you see append num. I see an sprintf, I see a string length. What are these doing in my code? I didn't do any of this stuff in here. And then I find GNU CXX verbose terminate handler. And I was like, makes sense. That's what's happening. Does everyone else have an idea of what's going to happen? What happens if you throw an exception and it hits main? You get this nice message. Terminate called after throwing an instance of my error. The code bloat seems to be coming from rendering this string. So check this out. What can we do about this? In 5 simple words, probably developers hate me. In 5 simple lines, you can eliminate all of this. So there's this thing in GCC and in Clang called weak symbols. They are variables that you can create that can be overridden by other code. Every variable you've probably ever made has always been a strong symbol. You have to mark them as weak in order to weaken them. But if you create the same variable name, the same symbol, it'll override the original. In this case, I overrode the original terminate handler with my own, which just does a little while loop here. That saves me 91% of my binary size. I'm down to 13K at this point, and now I'm pretty okay with using exceptions. 150K? Nah, it's not okay. But 13 kilobytes? I can do a lot with that. But we got another barrier. It still uses dynamic memory allocation. I still had to set up sbreak, and I know malloc's getting called. So I felt bad. I thought, well, I could just use exceptions normally, right? Well, it feels weird to teach my students not to use dynamic memory allocation. And then my mechanism that is in their software development kit uses dynamic memory allocation. I wanted to figure out if there was a way to at least escape this. Not that I have to solve it, but just at least escape it. So I looked at what does the assembly for a throw even look like? Where's the allocation happening? Turns out there's this function called CXA allocate exception. Cool. Can I override that? Yeah, you can. Same way as before. It's a weak symbol, so you just override it with your own thing. I'll go over why there's like an offset here and stuff like that later on as part of the talk. But yeah, I was able to at least give my own memory for that allocator, and now at least I feel like I have control over the memory and how much I can pre-allocate for my exception handling. And finally, the final barrier, the part that would make me feel okay with using exceptions. how can I handle the specter of RTTI? Because the thing is, my program is quite small right now. It's not doing much of anything. There's not that many types. But as the program as your application starts to grow, you'll have more and more types, more and more abstractions. This will start to grow and grow. So this is going to be a problem. So you have to figure out, can we disable RTTI? Or can we do something about it? Here's what I did. I just went, well, shoot, let's just change FRTTI to no RTTI. And let's see what happens. And we're going to go over a couple of these items, and we're going to have everyone vote on what they think is the right answer. So, and just a little note here real quick. C++ exceptions require RTTI to work, okay? So number one, the compiler tells you that you cannot use C++ exceptions with RTTI disabled. You get a little compiler error saying, nope, can't do it. Number two, compiler strips all RTTI information out of your binary. Sorry. Strips all RTTI information not involved with exception handling in your binary. And then number three, the compiler is completely silent, removes all the stuff. And if you call throw, it's UB. All right. Guys, think you guys got it? Who thinks it's number one? Raise your hands. Okay, I got one hand. Interesting, okay. I got two, all right. Who thinks it's number two? Interesting, okay, a good number of people. Who thinks it's number three? Are you guys all Rustaceans? Are you guys all infiltrating CppCon? Because here's the thing, why do you guys all assume that C++ defaults to UB? No, the answer is number two. Yeah, it was actually a really funny coincidence. It made it such that the only types that actually need to be in your binary are the ones that you throw. And I don't throw that many types, so it's not that much memory. And I think I have a little extra time, so I'll tell you guys, I don't have this in a slide, but I'll tell you guys what the memory layout of RTTI is. If you have an object that inherits no types, it takes up 2 pointers. If you have an object that inherits one object, it takes 3 pointers. If you have an object that inherits n number of parents, it uses up 3 pointers plus n number of pointers for the number of classes you inherit. That's it. It's not that much, to be honest, in my opinion. So at this point, I think, malloc's not really a big issue when it comes to this. I can override cxa allocate. The whole brings in the whole standard library. That comes from terminate. And before, it used to bring in IO streams, locales, basic strings, so it's gotten a lot better. ARM's done a good job. One last thing, that 150 kilobytes was back in the day, now it's like about 84 or 87. And for RTTI, I mean, it's still there, but it's quite minimal. So I was like, that's not that big of a reason not to use exceptions in my opinion. We still have more items here to look at. But at this point, I had seen enough. I was ready. I was like, this is great. I can move on with this. I changed all of the SJSU Dev 2 code over to exception handling. Moved all the macros, got rid of all that stuff. But in parallel, I was also developing another PR to completely move everything over to result types. I was going to compare and contrast, and whichever one I thought was going to work out better in terms of code size, I would go with. Or just at least in usability. And there's a little message here. You probably can't see it. Actually, you might be able to see that. I have a little message here saying it was decided to transition to exception handling rather than error return types. For large enough projects, exceptions are small in code size and faster when exceptions are not being thrown. Here's what I observed. When I was building up, I should put this back in. When I was building all my demos to make sure that my code was working appropriately, as I tested all my small demos like blinkers and hello worlds and that kind of stuff, they went up in size, which I expected. It's exceptions, should be bloaty, right? But then I tried out like a couple other projects, like a MP3 player that I had my students build as their like keynote or as their final project for the class. And those ones went down in size, which blew my mind. The code was meant for a micro that was 64 kilobytes. I think the binary size was around 56. I lost the code, so I can't demo it, unfortunately. But when I saw the code get down to 40-something K, my mind was blown. And I was super excited, but I also kind of kept it to myself for years. Mostly because, one, I didn't know if anyone would really care about this discovery or this little bit of information. I was also afraid of the Rust community coming after me, because if I showed anything positive for C++, I was certain they'd come after me and I'd get just completely washed on any social media. So I refrained from bringing it up until CppCon last year. This is when I attended the ISO C++ meeting in 2023. Yesterday, around this same time, Patrice was having his talk about things that are happening in SG14. Some water real quick. And he discussed the potential for the polymorphic memory resource vector, so standard PMR vector, if it could be used for embedded systems basically for embedded systems. And we had this discussion back and forth about this, and I told them, well, there's some problems with vector in the fact that pushback can't signal to you if anything went wrong. You could just terminate at that point, but I don't think a lot of developers would be happy with a panic if their vector just couldn't allocate. And then I tell them this. It's a shame that embedded devs don't use C++ exceptions because it would make their binary smaller. And he's like, hold on. That goes against all of common knowledge. What do you mean? And I explained him the whole story that I just explained to you guys just now. And he's like, do you have any data for this? And I'm like, well, I lost the old files, but I can synthesize it. He's like, come to Wednesday's ISO meeting and show off what you have. I was like, cool, we'll do. So I did spend like a good portion of the CppCon time working on that. And here was my hypothesis. My idea is, if I were to observe this, what could this mean? Well, let's think of the cost of result types. We can think about it as some A times N, where A is the average cost of the checks per function call, how many bytes it takes to do a check for a function call. And the N is the number of function calls that you check, the number of checked function calls throughout your entire code base. For exception handling, it is Bm plus E, where E is the cost of libunwind, the machinery you need to use to do the propagation. B is the average cost of exception metadata. And M is the number of non-leaf functions within your code. My assertion was that A of N was going to be greater than B of M. Well, there's one, you can't say that for sure, but you can at least say, and I think everyone can agree with me, that you probably, assuming your code gets stripped for all the functions you do not use, you probably call more functions than the number of functions in your code, right? So I thought, all right, well, at least those numbers are greater, have this equality or inequality. And I expected that I was going to get something like this, where we have this little number of checks on the x-axis, and then we have the binary size increase on the y-axis. And there'd be some crossing point where using exceptions becomes more optimal in terms of code size than using results. So here's the experiment. I generated a whole bunch of C++ code. It would randomly define a whole bunch of different classes with and without trivial destructors. It would create a sequence of functions that call each other. These functions would also create objects and call APIs on those objects. I had one file called except that would use exception handling and another one called result.cpp. These two files will be isomorphic to each other. They do the same exact thing except for the error propagation. And I made sure the code was just dedicated to just handling and focusing on error propagation, because from my experience, just to be real, I see more error propagation code than I see error handling code. I think you guys will agree with me as we go a little further along. Here's an example of what the code looks like. Here we have some function group. It's randomly generated. It creates a volatile variable because I need side effects. Otherwise, a lot of the stuff will get inlined. Even if you put like no inline, it gets real clever. GCC is really clever at just eliminating your entire program if it's in a single translation unit. Creating an object, calling some APIs, creating another object, calling some APIs, so on and so forth, calling another function. Same thing with expected, just with if statements to check. Here's what I got when I created a whole mess of these different files, compiled it down and looked at their binary size. Red line is the result types, the blue line is the exceptions, and the yellow line is the delta of size as you go with more checks. You probably can't see the number at the top here, this one right over here. I really love this number because it's 8,067, which is really close to the size of libunwind, if you collect all that together. And then here we have negative 16.5 times x. That would relate to the cost per check for every check you have inside your code. Not saying that it really is 16.5, but this is how Google Sheets calculated it out to be. Looking a little closer, you can see here, at this point there, that around 550-ish checks are enough to get you across that point, which isn't a lot in your code. I've definitely made single classes with up to 50 checks on its own. But I just want you guys to understand, none of those graphs were meant to convince you at all. I don't think they're very convincing. I just think they're there to show you something. If I want to convince you, I need to show you how exceptions work from throw to catch. So you guys can see how all of the different data structures interplay with each other and see what makes up the entire process. So let's get started. Things I'm not going to cover here. No nested exceptions, and anything other than table-based exceptions, because to be honest, I think that table-based exceptions are the best. All right, consider the following. We have some error. We have a function called foo. Foo calls bar and a try catch. Bar creates an object that's destructible. We call baz. Baz throws an error. There are three types of functions in exception handling. Leaf functions, which do not call any other functions, contain no destructors, contain no try catch blocks. We have trivial or transparent functions. They call other functions, they do not contain any destructors, and they do not have any try catch blocks inside of them. And then finally, we have reentrant functions. These are functions that call other functions, contain destructors, and have try catch blocks. They can be reentered in order to destroy objects or to handle errors. If we were to classify all of the functions we have here, foo and bar would be reentrant, and baz would be transparent. There are no leaf functions in here because it'd be boring. They don't participate in exception handling or error handling in general. So, in order to understand exception handling, you need to understand a little bit about how the calling convention in ARM specifically works. So, don't want to bore you too much, but there are 16 registers. R0 to R3 are used either as scratch registers or as input parameters to a function or return values from a function. Whereas R4 to R11 are preserved registers. These ones are registers that the function depends on to be the same state when you call a function and when you come back. Then we have a stack pointer, basically points out where you are on the stack, a link register, which contains the return address for your function, and your program counter, which tells you where you currently are in your application. Here's a little disassembly, don't get too, but at the start of foo, we're gonna push R4 and LR. What this means is we're gonna use R4 in our function. We don't want to destroy what R4 was before from whatever called foo, so we're gonna save it onto the stack. We're also gonna save the return address on the stack so we can pop it back later. We can do some stuff here. We can go over and set, let's say R4 contained the answer to or return type for this, or return value for this function. And then finally, we pop R4 back into its place, and we pop the link register back into program counter to jump you back. And that's how the calling convention for ARM basically works. Not really much else beyond that. So now that we have this idea of the registers in ARM, as well as basic RAM, we can kind of come up with what the state of the system would look like. And we have this little example here. We are at this location. Let's take a look at it. In the Itanium C++ ABI, when you call throw, it calls CXA allocate with the size of the object you want to allocate, in which case this is a byte. All the stuff here is for constructing that byte, as well as setting up the call to CXA throw. And the call to CXA throw takes the pointer to the thrown exception, takes a pointer to the type info for that exception, so you can actually compare it against your catch blocks, and then also contains a pointer to the destructor of that object. It is null pointer if it doesn't exist, like if you have something that's trivially destructible. Now, CXA allocate works like this. When you use it, it doesn't just allocate your thrown object, it allocates enough space for your thrown object, plus this thing called the exception header. The exception header is used by the unwind mechanism in order to remember the state of the system and to remember its progress as it unwinds. The parts within the exception header are this: a virtual version of your CPU. Exceptions, all they really do is calculate the previous state of what the CPU would have been if you had taken a different pathway. So we need to keep and record all the states of the CPU so we can jam it back into the CPU later on. We also keep a pointer to the type info because we need it for later on. We keep a pointer to destructor so we can clean up afterwards. And we have some cache which can help you to speed up things. I want you guys to understand that this is not the Itanium ABI exception header. They have their own definition for it. This is my own for my own implementation. You might be wondering, well, why not just call them malloc? Well, the reason why is for ABI compatibility and flexibility. See, if I resize the exception header in any way in the future, let's say we realize, oh, we want to cache more information to improve speed, or we realize, oh, we can remove some registers and we don't need to use those for the exception unwinding. If we use malloc and we bake that straight into your binary and we update it later on, the size of the header will be completely off, the unwind mechanism will be messed up, you'll have problems. The other benefit here is that you can do everything in a single allocation. Rather than having to allocate the thrown object, then in throw, allocate again for the exception header. So let's kind of go into my version of how CXA throw works. Number one, active exception. We need to set that so that current exception can work. It's a thread local stored variable. I know Craig told me I need to get rid of TLS. I am working on it, don't worry. Next thing you gotta do is take the thrown type. Because we know that the exception header is behind it, all this function does here, extract exception header, just subtracts the thrown type's pointer address by the size of the exception header, and that's what you have. From there, you can set the type info, you can set the destructor, and then finally, we can do a quick, immediate unwind of CXA throw to get ourselves into the state of whatever the CPU was for the caller of this function. So after that, we get something like this, where our program counter is pointing to CXA throw, because that's where we are currently. Our caller is Baz, that's what called us. Our stack pointer is initialized, and you see this little dark, yes, that's visible, cool. See that little dark orange area? That is an indicator of where the stack is currently. And these other registers, R6 to R12, I don't care about, we're not gonna use them in this demonstration. R4 and R5 are somewhat unknown, and we have a couple other items here who come from the input parameters here. One of the things that it has to do to unwind is to take the link register and put it back in the program counter so we can do our evaluation from that point. And then finally, we raise the exception. From this, we have a couple of steps. So number one, we start off the circle. We go and we locate the exception entry. The exception entry is information about a function, about how you unwind it, about if there's any destructors that need to be called, as well as if there's any try catches that need to be handled or evaluated. From that bit of information, from that entry, we can ask it, hey, should we refuse to unwind? Such as, are you no accept? If true, terminate. If not, check, are you reentrant? If false, unwind the function. But if it was true, evaluate the function. Check to see if you should enter it. Hey, did I match up with a catch? Maybe we should enter it. Or, hey, is there destructors to call? Maybe I should enter it. So from here, we enter the SAD path. From the SAD path, we have two ways of going. We can either hit a function called CXA cleanup end. This is what's called in order to get you back into the exception flow if you're calling destructors. Or you can hit a function called CXA end catch, which brings you back into the happy path. So now that we've gone over how this whole little mechanism works, we can go to the first part here, which is locating the exception entry. So here's what the exception index looks like, with a couple of symbols called index start and index end. Each entry in the index is 8 bytes in length, as defined by the ABI. The first 4 bytes is the function address. Technically, it's an offset to where your function is. There's reasons for that, good reasons, but it's the function address. The next part, another 4 bytes, would be the offset to the exception data. Now, before we go any further, we need to talk about what the ordering of the index is. It is ordered relative to the presence of functions in your code, the ordering of functions in your code. So if your code starts at address 0, and the first function at address 0 is foo, and the next one is bar, and the next one is baz, and the order of the exception index will also mimic foo, then bar, then baz. This way, if my program counter is somewhere in the middle of one of them, I can do a binary search to find where that entry is. And all I have to do is check one entry will have a function start, other entry will have another function start. If my program counter is between these two function starts, it tells me that I'm in the function to the left. The way that the structure works, you have a uint32, it's an address, and the other 32-bit value is a tagged union between some metadata or inline data. The most significant bit is what tells you whether or not it is one or the other. So we're gonna go over the inline data first. So let's imagine you take a transparent function, doesn't have a destructors or any try catches in it, and you label it as no accept. What that does is it replaces the offset value that would normally be there and replaces it with the number 1. The number 1 signals to the unwinding mechanism, hey, if you see this and you need to unwind it, simply call terminate. You can also embed the unwind instructions for the function directly into the index if there are only a few that are required. So if you need 3 or less unwind instructions for your function, and it's transparent, you can inline it directly into the exception index. And this is done in order to save memory. And now we're talking about instructions, we might as well go into it. So we're not gonna go into the details of how all these things work, but for the most part, the instructions are 8-bit segments. One thing to also know about ARM is that all of their instructions, if it's ARM 32 and 64, it's 32 bits. And if it's Thumb 2, it's 16 bits, and some instructions are 16 bits or 32 bits. So 2 bytes or 4 bytes. unwind instructions don't have to do much. They have to subtract the stack, pop some registers, and that's about it. So they only need like a byte of information in order to represent them. So they're a compressed version of a simulated version of returning from a function. The ARM exception ABI document states that most functions fit within 3 bytes of unwind information. And the longest you can ever have for any function that you could possibly make on ARM is 7 bytes of unwind instruction. So we have instructions for adding to the stack, subtracting from the stack, popping registers, setting the stack to another register, finishing, saying, hey, we're done with the unwinding, and then finally refuse to unwind, which will be called if you did cleanup and then had to then discover you needed to terminate your application, which can happen. So now we can go into the details of what these things are called. They're called personality data. The most significant bit of that inline personality data is this bit here, which is 1. If this is set to a 0, it means that this is an offset. If it's set to a 1, it means that this is inline data. Bits 28 to 30 are reserved. Bits 24 to 27 are the personality index. These personality indexes tell you about the format of the rest of the bytes to come. If it's 0, then the next set of bytes in this 32-bit word will be instruction 1, instruction 2, and instruction 3. If the index is 1 or 2, you'll use a long personality data, which gives you a length for the number of additional words for unwinding this particular function. Now, no, this can actually only be 1 to 2 because they found out that you only needed 7 instructions maximum, which is actually kind of sad because I look at this and I think to myself, we don't need to have the length there. If we had removed the length, then it would have moved up 1 and we wouldn't need the padding we need of the finished bytes here. That could have saved us 4 additional bytes, but we can't have nice things all the time. Now we have everything we need to know in order to unwind BAS. So we do a binary search through the index, we will find its entry, and then we will evaluate the inline data. So we check here, we look at the most significant byte, it's 1, it's inlined, personality is 0. The only instruction in here that means anything other than finish is this one here. Pop registers R4 to Rn, some range, and the link register. So after we execute this, we will see that bar 14 is put into the link register, and bars, the function bars R4 value, has been moved into R4, and the stack pointer has been moved up appropriately. Now we're going to do the same thing for bar, but then we realize it's reentrant because that is a structure to call, so we can't do anything with this. We need to go a little further. So we are here. Now we can look at the exception table. With the exception table, when you look at the index, you'll get an offset. Let's say it's 2,000, negative 2,000, 2,304. We use that offset from the location of this data member, this object here, to locate one of these items inside the exception table. Think of the blue items as being like the long personality data, and think of the red values or red boxes being GCC language-specific data area. Now, what does that mean? Language-specific data area is something that the Itanium ABI added in so that you could support, or we could support, throwing exceptions through Java and C# and C++ and have them all cooperate with each other. Yeah, we have support for that. It's one of the reasons why the normal GCC exceptions is kind of slow. They have to handle Java and other languages, even though that might not be anything, you might not be using Java in your code. So you could technically take a C++ API function call, pass it over some foreign function interface to Java. It could do some stuff, call that API. If it throws, it'll propagate through C++, through to Java, back over to C++. What's cool is that GCC can just leverage this same thing for C++ itself. So it created its own language-specific data area in order to make a generic format for how to handle exceptions that work across all processors. So here are the sections of this data. The first part is the personality function. This is the function that knows how to handle the data underneath it. The next part is the personality data. It's the unwind information. The next part is the header, which tells you how to encode or decode these sections here and here. We have the call site table, which contains all the scopes that matter in your code, such as the scopes you need to know in order to destruct stuff, as well as where the try-catch scopes are, or where the try scopes are. The action table provides order to your catches, because the order of your catch matters. And then finally, we have the type table, which holds a unique set of the types that are thrown in your function. So if you throw stood expected catch stood expected, stood exception 5 times in your function, you will only have 1 entry inside this table. So this will be an offset to the function. We don't care about this one. I override this one anyway in my runtime. For this one, it's just the personality data, just the same thing we went over before. And before we get into the header, we have to talk about this encoding called leb128. Leb128 is a variable length encoding. What it allows you to do is, let's say we look at these 2 bytes in sequence. We can take a look at the most significant bit of the byte and say, hey, if it's a 1, that means there's more data to continue. If it's a 0, it means you have finished all your data, you finished hitting the end of your number, concatenating everything together, now you have your number. This allows you to represent small numbers with small amount of data and big numbers with necessary amount of more data. So the header works like this. The first byte in the header is almost always on any embedded system going to be FF, just because it means total MIT dwarf information. That stuff gets stripped out anyway, so it's always going to be FF. The next byte will tell you how the type table is encoded, such as being position relative, which is normally the case, or these will just be absolute addresses. The offset here represents the location from this location here to the end of the entire language-specific data area, which is where the type table exists. Then you have an encoding for the call site, which could either be leb128, or it could be a UN8 or a signed 16 or whatever. And then finally, this tells you the length of the call site from the end of the header. From the call site, it gives you 4 fields: start, length, landing pad, and action record. Start is the location from within the assembly of that function down. The length is the range from that location. If your program counter is in between that, that means you're within this scope. That means that that landing pad and that action record correspond to you. The landing pad tells you where to end up in the function when you're going to re-enter it, and the action record can either indicate conditional jump, can indicate unconditional unwinding, destructor calls, or it can indicate a location within the action table. And you'll have n number of these. Some code to kind of show what it looks like. You have a function called read encoded data. You have a pointer that you can update. We have the call site format that we use to grab the information out. We get the start, the length, the landing pad, and the action. And if our program counter is in between that range, we break out of this while loop. If its landing pad is 0, we return early and just say unwind that function. No more to do here. From here, we can actually execute destructors. We know enough now at this point. So let's say we get the action number 0. And in some cases, if your type table doesn't exist, it'll give you this value 0. So this is another thing you can check for. In order to jump into the code, we take the start of the function plus the landing pad. We OR the least significant bit with 1 because it's a RMABI security thing. I think it's security. We assign the destination into the program counter. Then we have a special function called restore CPU state, which reads our virtual registers and populates them into the CPU. This will jump us into this location. Oh, I'm sorry. I'll get there in a second. So here we can kind of go through the encoding here. Every row in this diagram is a 4-byte word. We have the offset, we have the unwind instructions, we see dwarf omit, we see this thing's position relative, the offset's 0. We can start decoding this about 4 bytes in size. Start is at 0, the length is 28, and our landing pad is 30. Notice that our location is bar plus 14, so we're within the range of 0 to 26. Therefore, now all we have to do is set our landing pad to 30 and jump into the code. So here's what it would look like. I'm going to zoom in a little bit, and you'll see here that we have the first instruction here, add stack pointer plus 4 put into R0. Remember, R0 to R3 are for the input parameters of the function. We're just setting up the location of that object from the stack in the first parameter so we can call this destructor. Then finally, we call CXA cleanup, end cleanup, to recover the exception object, to set the state frame unwind, and to continue raising the exception. So it kind of just goes like this. Go from here all the way through, make your way to unwind, and continue the propagation. Oops, daisy. Go change that real quick. I lost my cursor. There we go. Cool. So after this happens, just know that the data underneath the stack of that object, or underneath that function, is now undefined, because destructors can use stack memory, and they could change up whatever's on the stack prior. So if you're going to hold something underneath in the stack, that could be destroyed. So after executing the destructor, oh, this is actually one other thing about executing destructors. You can have multiple landing pads depending on what area you are in your code. Such as if you know that you only need to destroy this one object, you can land over here. But if you're later on in the code, you can land here, call the first destructor, call the next destructor, and clean up. Now we just have to unwind bar, pretty simple. We do the same thing we did before. We use the offset value to go back to the LSDA data. We can just skip the first pointer and go straight to the unwind information. Here, we have personality 0 again. The first instruction tells us to add to the stack 12 bytes. So that would be move from this location, this is where our object used to live. Move this guy up. And then finally, we're gonna pop R4, R5 in the link register off the stack. That'll look like this for the first part of the code. And like this after we're done executing the next unwind instructions. Now we're ready to jump into foo, because foo's all set up. We are now pointing at foo. So now we're here. And now we need to look at the type table and the action table, because this will finish up the entire thing. So from here, the type table has a unique set of all thrown types. And if there's a null pointer in the type table, it means catch all. So catch dot dot dot. The action table is a little more complicated. It basically encodes the sequence of catch blocks for every single try. And each one of them has a number called a filter number. The filter number is the negative index that you use with the type table in order to access its elements. I should have showed that before, actually. The way that this works is that you get to the end of the type table, and then you go backwards to find all of your pointers. And if any one of the type info values, the pointer of it matches the pointer of the thrown type, those types are equal to each other. I think people think that you have to do like string comparisons to do like catch comparisons. No, you just gotta check the pointers. If there's multiple types and you have some hierarchy, you have to do something more complicated. Won't go into that now, but as simple as this, you just have to check the types. Check the pointers. If you get a 0, it means catch all as well. They have catch all encoded in 2 ways. And if you see 0 for the end of, oh, I'm so sorry, I skipped over a section. After the filter number, there's this thing called the next record. This is how you know, this is what guides you through until eventually you hit the end. The next record tells you from this location here, subtract your pointer's position up that amount, and then read again, and do it again, and keep doing that until you hit 0. And yeah, if you hit an end of record equal to 0, that simply means no more records at this point. And if you hit 0 end of records and there's nothing that matched, that means you should simply unwind the function. There's nothing there for you. If you do find a catch that matches, what you'll do is you'll set R0 to the exception object address, you'll set R1 to the filter number, and you'll set the program counter to the function address plus the landing pad or 1, and then you set the state. So to kind of show off what this would look like, we have here the end of the type table, which is 13. So from this point here, it'd actually be 13 bytes to get to the end here. We have the call site, which is 4 bytes. We know that foo's at 10. We check the call. We check the start and length. We're within the boundary. Our landing pad is 16. Our action record is 1. If the action record is 0, it means unconditional. It means call destructors. So we have to offset it by 1 in order to get the true offset into the action table. We look at filter 1. We do a negative access of the type table. We find this type. We compare the thrown and the caught type. They're equal to each other. And now we're ready to jump in. We now know it's time to jump into the catch block. So from here, it'll look like this. And also, it's a quick little thing. I don't know if anyone knows this, but catch blocks are switch case statements. At least in Itanium, they're just switch case statements. So the filter number is your switch value to which case that you are. So here we compare R1 with the number 1. And if it is 1, then we simply just pass through this little line here. It's branch if not equal. We enter a function called CXA begin catch. This will look at R0, which has our thrown object. It will set the exception to handled, and then it will return back the actual thrown object. From there, we'll do some stuff with it. We'll call CXA end catch, which will do the work of deallocating our object. And we'll also do the work of, calling destructors and deallocating our object. If it's not equal to 1, let's say we got in there somehow with some weird filter number, we will then jump to this location here and begin unwinding further. And that's pretty much it. That's C++, that's exceptions in ARM, GCC, pretty much complete. There's a lot more details to it. I'm obviously not gonna go over all that and bore you guys to sleep, but that's pretty much it. So now that we have all that information, we can go over what the space costs are for exception handling. Here's a table. I'm going to fill it out. So, number one, I wrote a couple of assumptions. Number one, we're going to assume that all the code's being compiled for code size, because otherwise that wouldn't really make a good benchmark. Number two, I'm going to assume that most functions that almost anyone here has written does not exceed 16 kilobytes in size, and that's like the instructions for it. To give some basis for that, I took Firefox a while back ago, took its debug build, dumped all of its functions, and looked at all their sizes. There are 253 of them that are above 16 kilobytes, and 325,000 that are below. So I think it's quite rare to find functions that are greater than 16 kilobytes. I'm also going to assume that between the number of catch blocks and objects that need destruction, we're going to limit and cap it at 63. There's a reason why I chose that number. Oh, and everything uses lab 128 because it's the most compact way to hold all this information. So first off, exception index, as defined by the ABI, is 8 bytes in length. That's it. Personality data, 4 bytes, as defined by the ABI. Long data, maximum of 12 bytes because of the unfortunate length 1 or 2. Catch blocks, gotta get a little deeper into the assembly. There are a couple things that need to happen for a catch block. Remember, it's a switch case. So we have the compare, the branch, compare, branch, the begin catch, which if you look here, it might be a little hard to see. Compare is only 2 bytes of information. The branch, if not equals, is only 2 bytes of information. The branch and link is 4 bytes, and the other, branch and link for begin is 4 bytes, and then the end catch is also 4 bytes. So it costs about 12 bytes in total for every single catch you have. For the cleanup regions, they are 6D plus 4. You need 2 bytes to set up the stack or set up the input parameter for the destructor. That branch and link is 4 bytes, so you need to have 4 bytes for that. You need that many for every single thing you're going to destroy. And then we have an additional 4 bytes for the final call to CXA cleanup. So that's where we get 6D plus 4. For the action table is 2 times A, where A is the number of catch blocks you have in your code. The range of a lab 128 number can only be between -64 to 63. So because of that, and me kind of having that constraint that I gave us, we cannot have a filter number that exceeds that. Therefore, we only need 1 byte of a filter number in order to represent that filter number. And because we're only using a single byte of information, the next record should never exceed -3 ever. It should always just be -3, -3, -3. For the type table, the size for that is 4 bytes for each pointer times t, which is the number of unique types in your function. And then for the call site, it's between 4 times the number of call sites you have, or 7 times the number of call sites. And this comes down to the other constraint that I gave, 16 kilobytes. 2 ULEB 128 values put together is 2 to the 14. 2 to the 14 is 16 kilobytes. So I can ensure, as long as my functions never exceed that all my call sites, the start, length, and landing pad, start. If my function cannot exceed 16 kilobytes, my start can never be beyond 16 kilobytes. My length can never exceed that either. My landing pad can never exceed that either. So we are constrained by the 16 kilobyte length. The action record, because of the other constraints we had before, is limited to, I think the maximum size the action table can be is, so here, 128 bytes, so that'll always be a single unsigned lab 128 value. Got lucky there, could have been off by 1. I'm going to skip this section because I hate, every single time I practice this one, I hate explaining it because it has a lot of math included in it. Basically, I have to deduce, with all the other constraints, why this particular table would be confined to only 5 to 7 bytes. But I'm going to do a paper on all this stuff later on, so if you guys really want to look into the details of this, you guys can look at that paper in the future. But suffice to say that the header can only be 5 bytes or up to 7. And here are all the things listed out inside of our table. A couple of examples. For trivially unwindable functions, if they don't have any destructors, don't have any try catches, and they're not like doing anything too extra, 8 bytes of information is required to handle this, on top of whatever is needed for the function itself. For a function with a single destructor scope, this will be about 34 bytes. You have the entry, which is 8 bytes, then you have the header, which is 5 bytes, probably not gonna be 7. Personality is 4 bytes, call table could be 4 bytes, maybe you need extra padding to make sure we're word aligned, so it's 3 extra bytes. Then we have 10 bytes for the landing pad, 34 bytes. Just add it on up. For time, we're not going to go into the details of this, but basically, if you add up everything we kind of talked about before and add it into the equation for everything that, all the different models that I had, you get to a minimum of 47 bytes if you have a try-catch in your function. So yeah, try-catch is a little expensive. Now, let's take a look at the space costs of return type error handling. Here's a quick little example. We have some function called none, means it doesn't do any error handling, or nothing there at least. It has 3 different functions it calls. Each one of these is fallible. Each one of these can throw an exception. And the number of instructions required to do this is just about 8 of them. What happens if we use setExpected? Or code will turn into this. I even put unlikely here, hoping that it would do something. I removed it, didn't change a darn thing. But here we're calling the functions, taking the values, doing what we need to do. From there, this assembly blows up to this. Whereas for every single check, I want you to look a little closely. I don't know if you can see this, but function 1, branch link to function 1, afterwards we have a load word from the stack pointer, from the object that we got back from this value, or set to, this, to the function. And then we have a compare branch if 0, which would jump us to this little area here, which is the error return path. So for every single check you have in your code, it costs you at least 6 bytes. In this case, 4 bytes for the load of word, and 2 additional bytes for every single one of the branches that you need to make. But you think to yourself, okay, setExpected, too heavyweight. We're not going to use that. We're just going to return back a bool. Isn't that okay? Yeah, kind of. It gets you down to 4 bytes. I will say that this instruction here may make you think, oh, well, it's only 2 bytes there. Well, that instruction is very limited in its scope. The reason why the compiler didn't reuse it over and over again is because this game can only offset you so far. So in general, returning back bools and checking them still costs you at least 4 bytes per time you do it. Let's consider Rust. Here's some code. Rust is really good at result types, so they should be like perfect at this. Nah, it's the same as setExpected. Pretty much. It's not that much different. The code gen's a little smaller though, which is great, but it's almost identical. Actually, it's pretty much identical to setExpected. But funny enough, if you make the result type a U63 versus a U32, it gets as small as bool. That's cool. But we still have that cost there. But for some reason, there's a weird optimization that pops up when your object gets too big. But in general, it's 4 bytes per function call. And that leads me to my conclusion. I'm going to discuss distributed and centralized error handling. What is distributed error handling? This is where you distribute your error handling throughout your entire code base. If-else branches, all that other stuff like that, out parameters, all of that. Whenever a function calls a fallible function, it has one of two jobs to do. Either A, propagate the error, or handle it itself. Whereas on the flip side, we have centralized error handling. This is a form of error handling where we have a central mechanism for propagating the errors. All the code that is inside your code base does not need to do anything special in order to participate in error handling. They simply just do what they normally do, and the exception mechanism will handle it for you, or the centralized error handling system will handle it for you. I like to think about this kind of in the same vein as the USPS or like having postal systems. Rather than having everyone else manage delivering their own stuff, we have a system for that. Exceptions are an example of this. Oh, and lastly, normal code and error handling code are separated in different domains, so they don't really clash with each other. So you can kind of view your code as the happy path and the other part as the sad path. Here is my claim. Centralized error handling schemes have an advantage in terms of code size compared to distributed error handling. Why do I say that? First thing, branches are not free. You have to pay for them every single time you use them. Let's say we wanted to add the set of 5 function calls. Let's say they're all fallible. I'd have to pay 4 to 6 bytes each time I call these functions to do a check. Whereas if I just use exceptions, I'd only pay 8 bytes total for this particular type of function. Here's another little example of this. Kind of think of like this is the memory usage and having the function and the SU personality data, and then the cost of each compare and branch. Remember, only 4 bytes in this case for each one of these. But I will be I'll be a little generous. If you do use a try catch, that's the cost of about 12 to 11 checked function calls. So, a little expensive, you know. But here's my next point. Most functions are trivially unwindable. Think about this for a sec. At least for the code that I've written and the code I've seen around, I have found that there's far more code that actually propagates errors versus handling them. And for a lot of embedded people, I bet you're writing a lot of objects that don't really need non-trivial destructors. Don't need to kill it memory, we don't use heap. And maybe you're gonna have a mutex lock, that's a little special, but in general, we're probably gonna use those very sparingly in specific places where we really need them. And I remember talking to Jason Turner like a couple months ago, and I asked him, hey, I need a way to figure out like any other examples online that I can look at. And he said, well, take a look at Audacity. Audacity has 1,054 C++ files. Only 39 of them have catch blocks in them. A total of 60 catch blocks and 69 catch blocks were found in the source code. Out of 1,777,000 functions, 50 of them actually had a try-catch. And the total cost for Audacity for the amount of memory used up for exception handling is about 15 kilobytes for all of Audacity. Well, let's be more extreme. Yeah, the previous example said that, what was it, like 0.028%? Let's make it 5%. Let's make the number of functions that allocate objects 25% of our code base. Let's set the percentage for trivially unwindable functions to 55% and 10% to leaf functions. I feel like this is decently generous. Maybe you have a different idea about this, but I think that this is reasonable. So let's kind of come up with an average size for each one of these. For the try catches, I'm just going to give it an average of 64 bytes. Its minimum is 47. Bump up a little bit, say 64 bytes. For my cleanup functions, at default, the minimum is 34 bytes. Let's move up to 46. Trivial functions, I said this is 8, purely because of the fact that long unwind information is kind of rare. So just 8 bytes for this one. It's going to be inlined. And then leaf functions do not participate in exception handling, so their metadata does not exist. There are 0 bytes for each one you create. Let's add it all up. This 8,000 here is meant to represent libunwind and the cost of using it in your code. We add up all these numbers and we get 27,100 bytes. Cool. It's a bit much. Now let's compare it to the number of checks in our code. Let's say that we're going to exchange this for using result types. And let's say that for every check we have, it costs us 4 bytes. How many checks do we get? 6,775. That's a lot of checks. But across 900 functions, it's kind of small. I don't know, 7.5 functions per function call before you end up in a region where you might as well just use exceptions initially. That seems a bit restrictive. Also, keep in mind that this number here is excluding epilogues, all the other return paths in your code. This is just for the code for checking the functions. And this is the best case scenario with 4 bytes. It can't get any better than this. If you can figure out a way to make it better than this, please tell me about it. That'd be really cool. Let's choose 6 bytes for use instead expected. Now we're at 5 checks per function call. Shoot, let's add in 2 additional bytes to represent what the epilogue cost would be. And now we're a little bit less than 4 checks per function call. And that feels really restrictive because I've written a lot of code that I like to call functions. I don't feel like being restricted from calling functions should be a thing when I'm trying to develop. So here's my main point. How does C++ exceptions enable smaller binary sizes? Well, in a couple of ways. Number 1, it reduces the code gen when calling fallible functions. Number 2, the unwind information scales with the number of functions you have and not the number of functions you call. And remember, the number of functions you call is going to be larger than the number of functions you have. Number 3, it eliminates the additional return paths. You don't need as many because you're not trying to return every time you call a function. Also keep in mind that there's been a lot of effort in the past with the Itanium ABI and the ARM exception ABI to compress all the instructions so that they're as small and as small as possible. And then finally, you only pay for the mechanism once. You pay that 8K, or at least with my unwinder, which is like 4.5K. You only pay for that once, and then you're done. And the sad part about this is not even exceptions' final form. Exceptions can be smaller. Look at this. Why do we need the dwarf information omitted, or why do we need a type table encoding? Why do we need a call set encoding? Why don't we make another personality function and just strip those out? Think about it like this. You really shouldn't do this, but you can technically pack the courts in the United States Supreme Court. You can keep adding more people. You can keep adding more GCC personalities. You can make personality v1. And that new one can have a smaller amount of overhead. Not only that, but like literally, I thought about this as I was making my way here. We could write a tool to convert one to the other. and keep the same information? And also, why do we call CXA end catch for every single catch that we have? Change it with a branch. Branch and link is 4 bytes. Branch, unconditional, is 2 bytes. Save 2 bytes per catch block you have. And there's like so many other ideas that I have rolling in my head that we could do to optimize exception handling in C++ in general. But that's just it for now. We have other talks that will go into that. So to me, I have to ask the question of what are C++ exceptions really? After so much time looking at the disassembly, looking at the metadata, and working with these data structures, I came to one conclusion, and that is C++ exceptions are code compression. They are a way to turn all of this into a little bit of that, plus 8 bytes of metadata. So to me, when I look back at this diagram of why you shouldn't use exceptions, the exception table and the exception code is the opposite of a problem. It is a solution. It's actually beneficial to use it. And I bet everyone's here is like, I don't care about code size. I want it to be performant. I want my stuff to be fast. You have anything about that? Well, lucky for you, my next talk will be on cutting C++ exception time by 88%. It was 76 before at ACCU, but then I worked on it a little bit more, and now we're at 88%. I'm certain I can get it to 92%, maybe 95. Don't quote me on that. You know, I'm trying my best here. But yeah, no, there's a lot of things we can do to improve the performance. Oh, and before I move any further, since I have a little extra time, does anyone know when the last time libunwind for GCC has been updated? Any of the stuff that's in there? I think if I looked at it for ARM, there were 8 individuals on the planet that worked on it, total. And that was around about 15 years ago. And then the main real chunk of it was 25 years ago. No one's touched this code for decades. So comparing my implementation of GCC, whereas if you're using std expected and you're unwinding 6 frames, GCC is about 27 times slower than that. Mine is still slower, but like 4.77, I think that's good. For 96 frames, which is kind of extreme, GCC is 21 times slower. It gets better as you keep going further. And then mine is at 2.56, slower than just returning from your functions. But I think I spent this entire time, this whole like 80 minutes or 70 minutes, talking about exceptions and how they're smaller, reduce code gen. But to be honest, I need to be honest with myself. Maybe some people who are really big advocates of exceptions have to be honest with themselves as well. Because here's the thing. Exceptions effing suck. Here's the thing. What does this throw? Be honest. Does anyone have an idea what this function throws? Absolutely not. But what would you do? You go check the docs. Go check the docs, says it throws some error. That's cool. But does it actually do that? Docs were updated about a year ago. We keep getting new updates from our vendor with new binary blobs. I don't know if they changed that. We go and email them. And we say, hey, do you throw anything else? Or do you return a different error code that we need to expect for? Back and forth, a week goes by. Finally get a thumbs up, yes. Nothing else gets thrown. You're good to go on version 5.10. Now I've upgraded. And now I have no idea what's going to happen. Yeah, you could say, oh, that should have been like a minor patch number or something like that if they changed that value. Maybe it should have been a major change. But the thing is, it doesn't matter. However they go about changing their versions, I don't know any longer. No one here knows. And to me, this is the ultimate problem with exception handling in general. Because of this, it's what makes people concerned about their code and how it will behave. It's because of this that people are trying to push away from exceptions so much. That's why we want to handle errors locally. The cool thing is that this is not like an impossible problem to solve. So I have another talk that will happen after this. This is the 3rd talk in the trilogy called the Exceptions Insights tool. I spent so much time looking at the disassembly that I noticed something. You know what's neat? When you return like a bool or you return std expected, it's not really easy to look at the disassembly and see what's happening. But whenever you throw, there's a call to CXA throw in your code. So here's what my tool will do. You pass me the binary, not your source code. Your source code doesn't know jack. Give me your binary, the thing you're going to actually execute. I will parse through your text section, what's called your code, your text section. I will find every single branch and link to CXA throw and CXA allocate because I can figure out how much you're allocating for every single one of your thrown objects. So I know the size of all your thrown objects, I know the type for them, and I know where you're throwing them. Now I can look through your exception index, and from there, I can evaluate where all the functions are and how they participate in exception handling. Find everything that participates in exception handling. From the index, I can now figure out where all your try-catch blocks are. And from there, what I can do is simply simulate throwing an exception, raising it through all points in your code. You have to provide me a call graph or we will generate it for you. We're still figuring out if we can do that. We can simulate calling and throwing all your exceptions and figure out which ones hit main, which ones hit no except functions, and which ones are caught and where they're caught. Because I don't think that this is an impossible tool to make, and I'm going to dedicate time to implementing this. And actually, I have some students here who came here who will be helping me with doing that. So before we finish up, I have two more slides. Special thanks to my mother who came out here from California to come see my talk. My beautiful fiance, Malia Labor, who's also part of the conference as well. She's also a C++ programmer. She can help me out with my slides. And really importantly, Herb Sutter, for a variety of reasons, but the main one is this talk here. This is the one that inspired me to do my talk. It's what inspired me to get interested in this subject at all. And on top of this too, I have to really thank Bjarne. I'm not going to put the full quote because I think it might be, but he wrote a paper called C++ Exceptions and Their Alternatives, where he basically was a counter to Herb's talk about a new form of exception handling. He said there's been little serious research on the topics of performance of exceptions and reliability of the resulting code in C++. So when I read that document many years ago, I thought to myself, maybe I could be the person to go research this. And before we finish up, I have a GitHub. I am not employed. I am working on this on my own accord. This is my own research. If you would like to support the kind of work that I'm doing in exception handling and on the Exceptions Insight tool and trying to minimize the code size for exception handling, you can consider sponsoring. If you are a grant-giving organization, you can consider sending an email over to estell.exceptions@gmail.com, NSF, Department of Energy, whichever one, don't really care too much. And if you're a company or you're part of a company that cares about exceptions and anything that I've spoken about is something that's useful to you, please tell me what issues you have with exceptions. Tell me how you're using them. I would love to have as much data as possible so we can build the right tools for the C++ community. Understand that everything that I'm building is going to be open source because I believe that this tool is useful, at least for me. I think that the Exception Insights tool and the other work that I'm doing will help promote C++ and keep it alive going into the future. So that's pretty much it. Questions? Yes.
Hi, that was a great talk. That was really interesting. It's and fascinating because it certainly kind of flies in the face of the conventional wisdom in terms of exception usage. So that's very cool to see. One thing that I am wondering about, this just kind of stuck in my head from the beginning. So we were talking about like copying the exception object originally,
yes.
like CXA allocate. Back at the beginning of the talk, we were using a static buffer for that in like an embedded environment. Are there any alternatives to that? I suppose, like, what happens if you fill the static buffer? Is there any fallback case? I guess that's like the one kind of unhandleable thing here is that as much as I prefer using exceptions myself, like it won't terminate your program if you run out of,
So there's two things. Number one is the Exception Insights tool along with building up some data structures. The next talks will talk about that and we'll cover those items. But I can tell you this, there is a way to allocate just enough information, just enough memory for every possible exception that your code can throw. It's a certain amount of blocks you need for every single thread you have, and you can go from there. But again, I have it in the next talk, we'll talk about all that stuff.
Okay, so if I could restate, you're saying the Exception Insights tool allows you to calculate an upper bound, essentially.
Yep, correct.
That's cool. Thank you.
Hi, first of all, respect. Seriously, awesome talk.
Thank you.
I work in the confluence of aerospace and robotics. And on the aerospace side, one of the things I'm required to do by regulation is demonstrate that I've covered all of the branches of my code from on-target runs to requirements. One of the things that concerns me about exceptions is how do I know what code has been generated and how do I trace that back to the requirements?
Oh yeah, no, okay, so kind of going back a little bit. So I didn't explain the Exception Insights tool too much, it'll be in the next talk. The goal is to give you, as much as we possibly can, a full global, kind of say like either a diagram or a full global insight into everywhere where exceptions are thrown, including in binary blobs that you've been given. That's why we look at the binary level. We don't look at source code because you might not always have the source code available to you. And we should be able to tell you which ones you have that are uncaught. The idea of the CLI tool would be exception insights, you give your L file, and it gives you a stat trace of every single exception that you missed. So the idea is to specifically solve this particular problem of whenever I do robotics work, I want to make sure that I've caught all the errors, and the errors that I do not want to catch, specifically ones that I want to terminate me, I allow. And we can have, we're still coming up with how we're going to write the tool to allow you to easily specify which things you allow to terminate you, and what things are allowed to should actually give you an error. As for where it's coming from, we'll at least be able to give you the locations where that data comes from, and if you have the debug symbols for those functions, we can potentially tell you what those debug symbols are or where those functions are, but if it's completely stripped, that might be a little harder.
Okay, thanks.
Yeah.
Hi, great talk. I have two questions. One regarding returning expected. Did you try the monadic functions like readability?
Oh, yeah. Same thing.
Macros and like what your students thought about it.
Oh, yeah. Oh, my students wouldn't use it. They actually found it too confusing. So yeah, they'd rather just use if-else statements. I tried showing them that stuff before, and once you start getting into like a lot of use of lambdas for like the or then and that kind of stuff, yeah, in general, the code gen's about the same, if not slight. The code gen should be around the same, and my students did not find it more desirable to work with.
Right, and the second question, do you plan to merge this stuff to GCC, or what's the...
Clang first, then GCC later.
Very cool, thank you.
Oh, one last thing to say is the improved exception runtime is a library. What you do is you bring it into your code base. I use Conan for this. You bring it into your code base, you have it as a dependency, and it will override all of the GCC implementation and replace it with yours. So you wouldn't even need to go to the next compiler version. You can just bring it into any of your applications currently. And it's backwards compatible. So like you don't need to change in your code to use it. You just kind of get the improvement. But maybe some aspects of how it's designed might not fit your use cases. Question.
Hello, thanks for the talk. It was really interesting. Does your exception analyzer tool like work across dynamic shared library function calls?
Yeah, so we have ideas of how we can approach that. We have not gotten there yet. We are thinking about it, and we know for a fact that if you're going to use that tool for any of your applications, you would need to run the analyzer on the machine it's going to execute on, because you need to make sure that we have ground truth of what shared libraries you are using. But we're figuring out if there's any other things that are going to be barriers to having it work better. So it is planned though.
I have a personal project that's been kind of back burner that I call POSIX-PP, which is an attempt to largely remove libc out from underneath C++ and replace it with a pure C++ layer for the system call interface. The place where I'm kind of stopped right now is all the research that would be needed to do what you just did. So thanks.
You're welcome.
Would you actually find the library that I'm working on useful once I get it done?
Potentially. Let's connect up and we can talk about it. Any other questions? Oh, yes.
Yeah, just I guess one of the obvious questions. Have you looked into x86, x64, and Windows?
Ooh, okay. All right, a couple things. All right, so we are planning to focus on ARM and RISC-V first. For x86, that will require some support from the community for us to have the resources to work on that, so just making that clear. As for Windows, Microsoft's going to have to contact me and talk to me about that, because if it's for MSDC, that's their own thing. If it's for like Clang and that kind of thing, it potentially could work. I have to look into that more, but I'm not certain. And I think we are out of questions. Thank you, everyone.